So this is part 6 of Programmer PIC Game. In this part I'll be covering how to create sound and play sound. As I go through the code, I will not cover the code that I've already covered in previous parts, and I'll just go through the code which has been added for this part. So if you want to see about the code in the previous parts, then the videos are available to go back and take a look at. So the first part of the code to be added will be the constants. This first constant defines a frequency for when you want the silent period and you don't want beeps to be playing. And then coming further down, I've got a flag in the app flags where I can define that sound is off or on, so whether a tune is playing or not. And then another flag which sounds very similar, where it says sound active, and this defines whether or not a beep is playing or not. So when a tune is playing, it has sound on and off to flag whether a tune is playing or not. But when a beep's playing, it has another flag just for the individual beep. So when a tune is playing, the actual function can tell when it's come to the end of a beep and when to start the next beep. Then the additional registers that are defined. So because I'm going to be using interrupts to actually generate the frequencies of the sound, I've got a couple of registers here where you need to store the value of the W register and the status register when you're in the interrupt, because an interrupt can happen at any time. And so when you return from the interrupt, you want to be able to restore these before you return. Otherwise, the program, when it returns the program, if it depends on the W register or the status register at that point, which it most likely will do, it will go into an undefined state where before the interrupt was called, it was one value, and after the interrupt was called, it was a different value, and you get a different result. And then I've got a set of registers here for the timer, so for setting the frequency on the timer and keeping track of what the frequencies are and scaling the timer. Then I've got a flag which I use, register which I use to actually define which tune I'm going to play. So in the EEPROM at the end, so with the LEDs, I had a definition of sequences of animations for the LEDs in the EEPROM. But in the tune, for the tunes, I've got definitions of different tunes in the EEPROM, and that fills up all of the EEPROM. I'll just skip down there now and I'll show you what they are. So in the EEPROM address 2100, I have the definitions for the sound, and the first thing I have is a frequency lookup table. So when I'm playing a note, the first part of the definition for a note will be the frequency, and the second part of the definition will be the duration, how long to play the note. So this is where I look up what the timer values are for each particular note that I want to play. And just below that, I have a lookup table for the tunes I want to, when I'm selecting levels. So when I want to select level 1, 2, 3 or 4, I can look up directly the level number in this table for where the tune starts. And then after that table, I have the actual tune definitions for the different levels. And the tune definition is the note, and it's followed by 00 to define the end of a tune. So for level 1, it just does a single beep. Then for tune level 2, it does a beep, and then this 10 defines the second nibble in that defines a silent definition. So it's a gap in the beep. So the first nibble will be the duration, just a duration of 1. The second nibble is F, so that looks up the frequency of F. And then on this bit, I have a duration of 1, but I have a little gap, so a silent period. Then again, it does a duration of 1 and no F, then end of tune. So it does 2 beeps for level 2, and then for level 3, it'll do 3 beeps, and level 4, it'll do 4 beeps. Then when you press toggle sound on and off in the game, this is a tune I play when the sound is toggled on. And then I've got a tune for what happens when the player wins, and I have a tune for what happens when the player loses. And that fills up the entire EEPROM area that I've got with the LED definitions as well. So there won't be any more definitions for this game for the that go into the EEPROM, because I've filled it now. So coming back up to the top, so that was a tune pointer. And then the next addition in this part of the code will be the actual interrupt vector. So in the previous code, I just had the return from interrupt opcode so that it would be safe if it ever got called with an interrupt. But now I actually need the code for doing the generating the beep. So I have to generate interrupt handle, and the first thing you have to do is store the W register in a register where you can restore the W register before you return, because interrupts can happen at any point in code. So you need to make sure the W register and the status register, which is stored here, and then I store it into this register there. You need to make sure that they're restored before you return. So if I go to the end of the interrupt handle just down here before I go through the actual interrupt itself, what I do is I have to restore the status. But when you restore the status, the process of doing that actually can change the 0 flag in the status, because I have to restore the W register as well. So after I've restored the W register, I have to check what the status bit well, I set the status bit first of all, then depending on what the status bit is in the area where I stored it, if it's a 0, then I will clear the status flag, and that sets it back to exactly how it should be before I return from the interrupt. So these bits of code at the bottom and at the top of the interrupt, they're handy for placing in whatever application you do. I use them in every application I do use which uses interrupts. So let's go through the code for the interrupt. First thing you should do is set the register bank to the bank that you want to use within the interrupt, because we've come from code and we don't know what the register bank was when this interrupt was generated. So you make sure it's set in the register bank that you want. And because it's in the status register and we've stored the status register as we've come into the interrupt, it doesn't matter when we exit the register, exit the interrupt routine, because that will, when we restore the status register, it will automatically put it back to the bank that it should be at after the interrupt. So the first thing I check for is a timer 1 interrupt. So I'm using timer 1 to do the frequency for the beeping. If there's no timer 1 interrupt, then it goes to the next area. Now I will have a timer 0 interrupt, but I've just got the address set up there for the later part when I come to do a timer 0 interrupt. So I don't actually do anything with that right now. And the first thing to do is check when I'm doing the frequency, is to check to see if the sound's active, because if it's not active, then there's no point in doing the doing the frequency. So it just goes straight to the end of this interrupt for the timer 1. Next thing to do is reset the frequency, the period for the frequency of the timer in these four instructions. So when an interrupt occurs, it's when it rolls over from FF to 00. So if I just left it, then it would do a huge period for the next part of the frequency. But I want it to be exact. I want the period to be exactly the same as the previous part of the frequency, so it creates a consistent frequency. So you need to set the timer to be exactly so that the next interrupt you get will be the right period. I'll check to see if what I'm currently playing is a quiet period, because if it's a quiet period, then I'm going to want to set again the timer frequency, but this time to the silent period frequency, and then I go to this place here where I skip over the code which I'm doing, where I'm actually controlling the speaker, so it will be a silent period. But if back up here it's not silent period, then it goes to this mark here, which is make sound. and then make sound. Because I'm using bidirectional ports, and this is a bit of a gotcha on the PIC microcontroller, when you change the port direction from input to output and output to input, it doesn't always update the GPIO register with what's currently on the output of the port. So it's important to read the GPIO register before you set the GPIO register using bit control, because otherwise it may not have the effect that you want it to have. But this is defined in one of the data sheets as what you need to do, but it's because it's not something that's obvious. This can be a real gotcha as to and when things aren't quite working right. This is one of the things you should think about. So what I do now is look at the current state of the speaker bit on the GPIO port, and if it's set, then I want to go to this turn speaker off area, and speaker off clears the bit for the speaker on the GPIO, so taking it low. Whereas if it was back up here, if it was on, if the bit was clear, then it goes down to here, and it turns the speaker on, and then it goes to the point at which it would do after turning it on or off. So the bit of code just here just toggles the speaker on or off depending on whether it's on or off when it enters this routine. So that actually generates the speaker generating the frequency, and then at that point I decrement the period count, so it'll only play the beep for a specified amount of time that that was in the definition for the beep. And if the period count isn't over yet, then it goes to timer end and it continues. But if the time count is over, then there's this second beep period count. So because one byte wouldn't be long enough to count for a decent period, there's two period counts, and that one also has to count down to 0. Otherwise it will just go, before it's finished the period, it will go again to this skip over to the end. But once the actual both of these counts are down to 0, and bear in mind that when the high count is has gone down to 0, the low count will then start off at 255 again. So it's going to be quite a long period, and then it will decrement the high count, and then it go through 255 counts to the low count again. But after that long period, it flags the sound as not being active anymore because it's finished either doing the beep or the silent period, and that's the instruction to the function which controls playing the tune as to whether or not to start the next beep. And then also at the very end, because this is the end of the beep, I make sure that whatever the state the speaker was in, it's always going to be off. And the reason I want it off is because I don't want any power going through the speaker. I want the speaker to be at the lowest power when it's in its off state. And this is at the end of handling any of these interrupts. What you have to do is you have to clear the fact that the interrupt was flagged by the PIC microcontroller, and then the PIC microcontroller knows that it can generate one of those interrupts again. The next bit is the hardware initialization. So there's a couple of extra things that you need to do in here in order for the sound. So first of all, you need to configure time 1 for interrupts. So tell the PIC microcontroller when the time 1 rolls over from FF to 0, then it needs to generate an interrupt and put us in the interrupt handler. And then a bit further down, because that's done in register bank 1, so when I come out of register bank 1 and go back to register bank 0, there's a bit of code that needs to be done using those registers. And that's to turn time 1 on. And set the prescale, so that there's no prescale definition, so it's not prescaling time 1 at all. And then I clear the timer interrupt flag, because if the timer interrupt flag, this is the thing that you clear after you've handled the timer interrupts as well. because if at this point the timer interrupt flag is set by any chance, then it wouldn't generate the first timer interrupt. So you need to make sure that's clear at this point, and that means that you're guaranteed the timer will start generating interrupts as it should do. And then after I do the software for the application reset, so after I've cleared everything, I only enable interrupts then, so that I know that when the first interrupt happens, the application will be in a consistent state where I know it's ready for handling interrupts. And there's two things you enable. First is the global interrupt enable, and then the peripheral interrupt enable. And you do that by moving into the intcon register. And then there's another flag which I clear for the other interrupts that I have, but I haven't defined those yet. But I've put that piece of code in the initialization because it's nice to have. Just make sure that if we're going to handle interrupts, make sure that the interrupt handler is in a state where it's ready for us to handle interrupts. So I come to the test harness. So this is just a bit of code which is just for this application and won't be called in the actual completed application. It's just for testing the functions that we're defining here. And the first thing I need to do is turn sound on. So by default on the actual game, when you're playing it, the sound's turned off and you don't need to press a button to turn it on, but we're simulating the button being pressed here and just actually forcing the sound to be switched on. Then what I want to do is I want to play the tune for this demonstration, the wind tune. I set that in the tune pointer, and that's all I need to do to set up a tune to be played. So everything would normally just play as soon as I've done that. But in my test harness, there's a couple of things I need to do. So this would normally happen in the interrupt, so this will get moved into an interrupt later. There's a monitoring function which gets called and just checks if the current beep is finished and the next beep needs to start, and that just gets called on each iteration of this loop. But apart from that, that's all the code that we need to actually demonstrate the sound function. So now I need to move on to the sound functions themselves. So for the sound, there's only a couple of functions which need to be defined. The first one is this play next beep, and that just, when you're playing a tune, this is what monitors for the end of one note and the beginning of the next note, or when the tune actually is completed. So the first thing it does is it checks to see if the tune is currently playing, because if it's not playing, then we don't need to do anything. So it will go on to this next beep marker and it will just return straight out. So if a tune is playing, it checks to see if a beep's currently playing. And again, if a beep's playing, then we don't want to interrupt that beep playing, so it just goes to the end of the function again. So if a beep's not playing, then it wants to get the next note. It does that by calling the read EEPROM function, because at the very top here, what I did was I read the tune pointer to see if it had a value in it, and if there wasn't a value, then it wasn't going to be playing, because it clears that value when it's finished playing that tune. But if there was a value in there, then that would be the address to read from the EEPROM of the next note. And then after that note's been read, it checks to see if there is if it's the end of the tune. And if it's the end of the tune, then it clears the tune pointer, which is the test up here, which says it's been if it's been cleared, then it's the end of the tune, and we don't need to do things. So that's what sets that up. So if it's not the end of tune marker, it goes to this label here, play next note, and that calls the start beep function, which is the only other function I need to describe here. And it increments the tune pointer to the next note, ready for next time it comes around and wants to play the next note. So this is the start beep function. Actually, this function can be called itself. If you just want to create a note that's not in a tune, it's just like a single note, then we have to just set up the W register, and in the definition, high nibble of that W register, if you put the duration of the beep, and in the low nibble of the register, if you put the offset into the frequency lookup table of the frequency you want, then it will play that beep for you. So I think I do that in the application at some point when I'm not actually don't want to play a tune, but just want to play a beep. But also as you've seen in the last function, the actual tune application calls this itself when it wants to play the next note as well. So when it's read from the EEPROM, the definition of the note in the tune, which is the same definition as described up here, it will call this function. And the first thing the function wants to do is check to see if sound's enabled, because if sound's not enabled, so if the player's decided that they don't want sound to be played in the game, then it mustn't play sound, so that will just skip to the end of the function at that point. It checks to see if a beep's currently playing, because again it doesn't want to interrupt a beep that's already playing, just as a safeguard. Otherwise it gets you'll get like some funny sounds coming out, and so if a beep's currently playing, it will skip to the end of the function. So I moved the beep definition, which is in the W register, into the beep len low register, and that's only there as a temporary thing because I'm gonna be using the W register, and I'm gonna ultimately change what's in the W register. I want to keep the original value of the W register so I can get to it a bit later. I also moved the W register into the beep len high register, which is where it's ultimately going to be used at this point. I swapped the nibbles around because I want the high nibble to be the low nibble, which is where I'm going to use it, because that's going to be the length of the period of the beep. And then I just mask that out, because what's now been shifted into the high nibble will be the frequency of the beep, and I don't want that in this. I just want the period, and so I'm masking that out. So there's a bit of bit shifting and going on here, and this is the AND statement is where the actual mask happens, and that's so now I've only got in the high register the beep len high. I also do the mask on the low register, so this is where I had a copy of the W register, and as I haven't swapped these round, in the low register is the frequency lookup value that I want, and now I've masked that out, so I've only got the frequency lookup in the beep len low register. I then move the frequency lookup base of the table into the W register, and I add that with the offset which I've just created just above, which I masked out just above in the beep len low, which is temporarily in the beep len low. So now I've got the frequency lookup table plus the offset into the table where I want it to be. So now I can call read EEPROM to read what the actual frequency is going to be, the frequency period value for the timer. And after I've got that back, I can put that into the beep frequency high value. And I can also, as the initial setting for the timer, I can place that in the timer. Then I clear the beep frequency low register, which I was only using as a temporary register just now. Just make sure that's clear, and timer 1 low register, I clear that as well. And beep len low, that's cleared as well. So of the 16-bit registers, only the top values I want to set, and they're now set to the values I want them for the beep. And so I can flag in the app flags that the sound should now be active, and that will start playing the beep automatically. I've programmed the code for this part onto this PIC microcontroller, and I put it in the socket, and when I do, it will show the animation of the LEDs for the last part, plus it'll also play the sound for the code for this part.